Understanding algorithm efficiency through time complexity analysis. In the world of computer science and software development, algorithms are the building blocks that power everything from simple sorting operations to complex machine learning models. However, simply knowing how an algorithm works is only part of the equation. Understanding its efficiency through time complexity analysis determines whether it can handle real-world problems at scale. Time complexity analysis provides developers with a standardized way to evaluate how well an algorithm performs as input size grows. This process enables programmers to compare different approaches objectively and select the most optimal solution for their needs without relying solely on trial-and-error methods. The fundamentals of Big O notation. Big O notation serves as the cornerstone of algorithm analysis by describing the upper bound of an algorithm's runtime in terms of growth rate relative to input size n. It abstracts away constants and lower-order terms to provide a clear picture of scalability potential. This mathematical framework allows developers to categorize algorithms based on worst-case scenarios rather than average performance. While other notations exist like omega and theta, Big O remains universally accepted due to its simplicity and practicality in comparing implementations. Why does Big O matter? Consider two sorting algorithms, one operating in O, n superscript 2, time versus another running in O, n log n. For datasets larger than 10,000 elements, the difference becomes exponentially significant. Understanding these distinctions empowers engineers to make informed decisions during system design. O. 1 Constant time operations. Accessing an array element by index takes fixed amount of time regardless of array size. O. Log and logarithmic growth. Binary search divides problem space repeatedly until solution found. O. N linear time. Simple iteration over each item in dataset required. O. N log and efficient sorting algorithms. Merge sort uses divide and conquer approach effectively. O. N superscript 2 quadratic time. Nested loops often result in this inefficient performance. O. 2 exponential growth. Recursive solutions without memoization lead to rapid resource exhaustion. Evaluating space complexity trade-offs while time complexity focuses on execution speed. Space complexity considers memory usage requirements for implementing an algorithm. Both factors must be balanced when selecting appropriate data structures and computational strategies. A classic example involves choosing between iterative and recursive implementations. Iterative approaches typically require less auxiliary storage but may involve longer code paths compared to compact recursive formulations using call stacks. For instance, an iterative Fibonacci implementation storing previous values consumes O, n extra memory while maintaining O, n time complexity. A recursive version without memoization has O, 2 time complexity but requires only O, n stack depth for storage. Common memory optimization techniques. Space-efficient algorithms leverage various optimization tactics such as dynamic programming, bit manipulation, or in-place modifications. These techniques allow programs to minimize temporary storage requirements without sacrificing functional correctness. Dijkstra's algorithm, for example, maintains only necessary information about current shortest paths instead of reprocessing entire graph nodes redundantly. Similarly, Quicksort's partitioning strategy rearranges elements within existing arrays rather than creating new copies for subarrays. Practical examples of algorithm performance comparison. Analyzing actual implementations helps reinforce theoretical concepts. Let's examine 3 common searching techniques with distinct asymptotic behaviors. Linear search scans each element sequentially until target value found. Worst-case scenario requires checking every element resulting in O, n time complexity. Binary search operates exclusively on sorted collections by repeatedly dividing. Search interval in half. Achieves logarithmic O log n performance, making it significantly faster for large datasets. Hash table lookup utilizes hashing function to map keys directly to memory locations. Provides constant time access O, 1, assuming uniform distribution across buckets and minimal collisions. Comparing these options reveals why certain algorithms become preferable depending on use cases. When working with unsorted lists where frequent insertions occur, linear search might still be viable despite higher theoretical complexity. Identifying bottlenecks through profiling tools' real-world application often necessitates profiling algorithms under actual conditions rather than relying purely on theoretical estimates. Modern IDEs and debuggers offer built-in tools that help pinpoint performance bottlenecks accurately. Popular profiling methodologies include using timers to measure exact execution durations for different algorithm variants, analyzing CPU utilization patterns through sampling profilers, monitoring memory allocation rates to detect leaks or excessive garbage collection events, tracking cache miss ratios to understand hardware-level performance implications. Data collected from these sources informs empirical validation of analytical predictions made earlier in the design phase. Sometimes theory suggests one approach will outperform another, yet real-world results tell a different story due to unforeseen constraints. Tips for conducting effective asymptotic analysis to ensure accurate evaluation of algorithmic efficiency. Follow best practices that enhance both qualitative and quantitative assessments. Begin by clearly defining what constitutes input for your particular problem domain. Pseudocode breakdowns aid in identifying key steps contributing most significantly toward overall complexity. Focus particularly on nested loops, recursive calls, and any branching logic that introduces exponential behavior. Create tables showing how operation counts change with increasing input sizes. Visual representations frequently reveal trends more intuitively than raw numerical comparisons alone. Always consider real-world limitations alongside idealized mathematical models. For example, disk I/O speeds can dominate processing times even for theoretically efficient algorithms handling massive files. Case study: optimizing matrix multiplication routines. Matrix multiplication presents interesting challenges for optimizing both time and space complexities simultaneously. Traditional naive approach runs in O(n) superscript 3 time, which becomes prohibitively expensive for large matrices. Optimization techniques include Strassen's algorithm reduces multiplicative factor to approximately O(n) superscript 2 at expense of increased constants and potential numerical instability. Caching strategies organizes memory accesses to maximize cache hit rates, minimizing page faults and TLB misses. Parallel processing distributes computation across multiple cores or GPUs, leveraging hardware acceleration capabilities. Sparse matrix handling stores only non-zero elements, reducing both computational workload and memory footprint dramatically. Each improvement comes with trade-offs requiring careful consideration before implementation. The choice ultimately depends on specific hardware capabilities, expected matrix dimensions, and tolerance for approximation errors introduced by alternate methods. Interestingly, recent research has explored tensor decomposition approaches that further optimize multidimensional array operations beyond traditional matrix-based methods. Emerging trends in asynchronous algorithm design. With growing emphasis on distributed computing systems, asynchronous algorithms now play crucial roles in many modern applications. Unlike synchronous counterparts that rely on global clock signals, these designs enable concurrent execution across diverse networked environments. Challenges arise from managing partial orderings among operations and ensuring consistency, properties similar to sequential execution. Researchers continue exploring consensus mechanisms and fault-tolerant architectures that maintain correctness guarantees under uncertain communication delays. Notable developments include event-driven architectures. Processes react to external stimuli rather than following predetermined instruction sequences. Microservices orchestration enables independent scaling of individual components while preserving end-to-end functionality. Stream processing frameworks handle continuous flows of data with bounded latency requirements. Unlike batch-oriented approaches, fault tolerance protocols implement replication strategies that automatically recover from node failures without disrupting service availability. These innovations redefine our understanding of algorithm performance metrics, since they introduce temporal variance caused by unpredictable message passing latencies inherent in distributed systems. Conclusion: mastering algorithm analysis equips developers with critical skills for tackling increasingly complex software engineering challenges. By systematically evaluating time and space complexities, professionals can identify optimal solutions tailored specifically to their project requirements. Continuous practice combined with hands-on experimentation remains essential for deepening proficiency. Engage actively with coding platforms offering competitive programming exercises focused explicitly on algorithmic efficiency improvements.